Hello, everyone, and welcome to today's lecture on n-body simulations. And I'm going to specifically focus a little bit more on stars near the galactic center and how we go about simulating those, because that's what I specialize in. Okay, so I wanted to start by talking to you about the overall goal of this lecture. So by the end of this lecture, I'm hoping that you are capable of, first of all, understanding the sort of basic terminology and concepts, the basic things that go into an n-body simulations and what sort of setup and settings are usually used for n-body simulations. So these are things like collisional versus collisionless n-body simulations, which Steve has already talked about a little bit. I'll talk a little bit more in detail about Poisson solvers. So these are some of the simplifying methods that are often used, the tree method or the particle mesh method, for instance. And then I will talk about orbit integration. So these are essentially, taking the forces that are on each particle and how do you compute the next time step and how do we go about integrating that. And then finally, I will talk very briefly about hydrodynamical simulations and how we go about adding gas on top of star particles to the simulation. And then more specifically, I wanted to go into detail about for each of these bullet points that I've talked about already, essentially what kind of settings are used to simulate stars near the galactic center and why we specifically choose those sort of settings and different Poisson solvers, orbit integration, things like that. And sort of the overarching goal of all of these is that you be able to read papers about n-body simulations at the end of the day and mostly know what's going on. So by the end of the lecture, I want you to be able to just go on the archive, and if you find a cool paper that uses an n-body simulation to talk about things, that you should be able to sort of understand mostly what's going on there. Okay, before I get into the sort of details of n-body simulations, I wanted to first talk to you about how n-body simulations work sort of in a nutshell. So here's the general sort of schematic picture. So you have a bunch of particles, and each of them, they have a position vector and a velocity vector at a certain given time. Based on that, we can use a Poisson solver, whatever we choose to use, to get the forces that are on each particle. So for these forces, we are essentially looking at the pairs of interactions between the particles. And once we have the forces on each particle, now we can use orbit integrators to come up with the next time step. So we use the particles, get the forces by using a Poisson solver, and then use orbit integration to compute the new positions and velocities at the next time step based on the forces that are on each particle. But as you can probably imagine, the overall issue with n-body simulations is computation time, right? Because we have n particles, each with n-1 interactions. And so this gets very computationally expensive really, really quickly. So one way to bypass this issue is if we can assume that the system is collisionless, we can sort of take this shortcut and invoke a potential on the entire system. And if we can sort of put a potential on the entire system, we can just calculate what the force on each particle is by just taking the gradient of that potential. And so we can sort of bypass that computation of n-1 interactions by invoking a potential, directly going to the force, and then just doing orbit integration to get the next time steps. So first, I wanted to talk to you a little bit about what is the criteria between collisional versus collisionless and what differentiates those n-body simulations. Okay. So in terms of collisional versus collisionless n-body simulations, we talked about this thing called the relaxation time, which is essentially the time that it takes for collisions to come into play and let the particles relax, right? So they're going to forget their initial conditions that they started with because collisions happen and they relax. And so this is the sort of relaxation timescale. And we looked at this equation that relates the relaxation time and the crossing time, which is shown here. Okay. And we basically said that if we compare this relaxation time with the lifetime of the system, we can basically say that collisions are unimportant if this relaxation time is much greater than the lifetime, right? Because that means that collisions are not playing a key part into relaxing the conditions of the particles And if the relaxation time is much greater than the lifetime, we can basically say that the system is collisionless. But on the other hand, if this is not the case, we have to consider a collisional n-body simulation. So what that looks like, I've already sort of talked about this a little bit, but we have n particles and we have to consider n-1 interactions. So you can probably see where this is going. Even if we invoke Newton's third law, this is going to be n times n-1 divided by 2 computations of the force, which is going to be of order n squared. Right, so this is going to be a very, very computationally expensive effort, especially as we take larger and larger n in our simulation. But the overall picture that I want you to have is if we have a bunch of stars like so, then what we're going to do is we're going to pick a star, let's say this one, and we're going to consider its n-1 interactions as shown by these white arrows. And then, we now have the force on this one particle, but now we have to move on and say, we want to compute the force on this particle. Then we have to once again consider its n-1 interactions. And so you can kind of see already, just based on the schematic, where the order n squared comes from. But instead of doing that, if we can say that the relaxation time is sufficiently large, so we can treat the system as a collisionless system, then we can use potential theory. So these are things that we've already talked about: Plummer's potential, isochrone potential. Basically, we can assume a common potential on the entire system and use that to compute the force on each particle. So this is going to be order n, but indeed you miss close encounters, right? Because that's the assumption that went into it. We assumed that the system is collisionless, so you're going to miss close encounters, which might be important in some situations to the evolution of the system. But the overall picture to have for collisionless n-body simulations is we have a bunch of stars again, but now we're going to sort of invoke this overall potential, this blob of potential. And for each of the stars, we can now just calculate the force on it by using this potential. So you can see that this is order n rather than n squared. So while collisionless simulations are much less computationally expensive, it is a big assumption to make because we miss close encounters and collisions, which, as we shall see in the next slide, are important for stars near the galactic center. Okay, so to figure out if for the galactic center we should use the collisional or collisionless n-body simulations, we have to calculate the relaxation time. So let's follow that for the Milky Way galactic center, for instance. So for the Milky Way galactic center, we know that there is around 10 million, 10 to the 7 stars within about a parsec of the galactic center. So we're going to use that as our sort of scale. So for n is equal to 10 to the 7, we see that the relaxation time to crossing time ratio is going to be about 10 to the 5 if we use this prescription here. But as we said, the nuclei's radius is about a parsec that we're considering here, which is a very small scale. So as you can probably imagine, the crossing time is also going to be very short. So within a parsec, the crossing time is just about 10 to the 3 years, which is very short in the context of astronomy, of course. And so even with this ratio of 10 to the 5, you see that the relaxation time is going to be about 100 mega years, which is less than the age of the Milky Way galaxy. So what this says is that because the relaxation time is shorter than the lifetime, we in fact have to use a collisional n-body simulation for the galactic center. And this is usually the case. So even if it's not for the Milky Way, when we usually consider the stars near the galactic center, we have to consider a collisional n-body simulation. So we can't just put a potential on it and call it good. Okay. So now we talked a little bit about collisional versus collisionless, but specifically for collisional n-body simulations, we need to consider Poisson solvers. So these are essentially based on the positions of the stars, positions of velocities of the stars currently. How do you compute the force on each of the particles? Okay, so the first sort of simplification that's often used is what's called the tree method, which is a very clever way of sort of simplifying the problem. So this is a 2D sort of schematic of what the tree method looks like. But in 3D, of course, we're going to be dividing the space into octants rather than quadrants. But let me back up. So this is, let's say this is the cube of the parent simulation here. we're going to first divide that into octants. So we're going to divide the 3D space into equal 8 cubes. And so that's going to look like this. And then you're just going to keep doing that until finally, when we get to the sort of leaves of this tree, we have a bunch of small cubes. And the goal is to get in each of the cube, either 0 particles or 1 particle is when the sort of division stops. So in each case, if a cube has more than 1 particle, we're going to subdivide that into further octants until we end up with a scenario where we have 0 particles or 1 particle. Okay, so now we have like sort of successfully mapped out our cubic volume of our simulation. And what we're going to do is when we collect these leaves and come back up to the parent simulation, what we're going to do is we're only going to store the center of mass of each of the cubes. And so at each process in combining the octant into 1, we're going to store the center of mass. We're going to store the center of mass until we come back all the way up to the parent simulation. So what this does is we can do a clever trick where if you wanted to consider the force on 1 particle, for all of the nearby particles, we're going to directly compute the force on it. But for the very far particles, we can actually say that, oh, we can approximate all of the total mass as being located at the center of mass of that particular octant. So for that particular particle, we're just going to group all of the far particles together into a single octant, a center of mass, and then calculate the force based on that center of mass. So it turns out that this significantly reduces the computational time. Specifically, the order is now going to be n times the log of n, which is much less than order n squared in the limit that n is very large. And so this tree method is a very, very clever way of sort of coming up with a way to not lose as much accuracy, but still be able to reduce the computational time significantly. Another method that's often used is the particle mesh method. So in the particle mesh method, we are going to actually put a grid onto the entire simulation, and we're going to interpolate the positions and vectors, the velocity vectors of each of the particles onto the grid. Once we do that, we can invoke a Fourier method. So if we Fourier transform this Poisson equation, which is shown here, we get something that looks like this, where, of course, the twiddle is going to be the Fourier transformed quantities. But essentially, if we interpolate the mass distribution, we can take the Fourier transform of that and then solve for the Fourier transform of the potential, and therefore get the potential and then get the forces on each of the particles. So if we do this, we also get order n times log of n if we use some sort of fast Fourier transform algorithm. But in fact, the computation time is usually faster than the tree method in most cases. But of course, the tree method and the particle mesh method have their own sort of advantages and disadvantages. Okay, but now we're going to talk about the galactic center specifically and what sort of Poisson solver is used there. And I have some bad news. It turns out that we usually just use direct summation. So we can't use the tree method or the particle mesh method when we're doing stars near the galactic center. So this is going to look like a double sum in terms of the computation. And so for each of the particles, we're going to consider each of the interactions, and then consider the sum of, in the case of Newtonian, the sum of GMM over R squared for each of the pairs. So n times n minus 1 interactions. Why we have to directly sum them instead of use simplifications like the tree method and the particle mesh method is because the length scales are much, much smaller than the size of the galaxy, right? So close encounters are going to be super important in determining the evolution of the system. And because the overall length scale is so much smaller than galactic simulations or cosmological simulations, we are essentially not able to segregate the far particles from the near particles. The far particles are just as important as the near particles, and therefore we can't do the simplification of center of mass in the case of the tree method, or the interpolation in the case of the particle mesh method. Okay, so Of course, as you can imagine, direct summation comes with its own limitations. And it turns out that because this is the most sort of computationally expensive way of doing the n-body simulation, n of around 10 to the 6 is currently the limit, even with today's technology. So that's the limit of the computation that we can do directly. Okay. So I wanted to take a brief aside and discuss this thing called gravitational softening, which is sometimes used. So gravitational softening deals with this very simple issue that close encounters are computationally more expensive because the gravitational force, if you look at the form of it, as the separation between the particles goes to 0, the force goes to infinity, which is a problem because, as large forces come into play, for close encounters, this becomes increasingly more expensive and increasingly more time-consuming when it comes to the computation. So here is what the potential usually looks like, right? So for each of the particles, we have something like gm over r, which of course goes to infinity as r goes to 0. But instead of doing that, for gravitational softening, we are actually going to add this softening function of r. So this softening function of r is, of course, not physical, but it makes the computation less expensive. And so we usually try to pick a clever sort of softening function that doesn't deviate too much from the real physics. So usual choice of this is usually the Plummer potential. So in this case, the softening function looks something like this. So we have a 1 over square root of r squared plus a squared type quantity. And so if we plug this into this formula here, we get a potential that looks like the Plummer's potential that we already talked about. So we're going to get a gm over square root of r squared plus a squared type quantity. And you might be wondering what this a is. So this a is what's called the softening length. Of course, this is just an artifact of computation. But this softening length is usually chosen to be 1 over 50 to 1 over 20 of the mean particle separation, as to sort of not mess with the overall structure of the simulation. But if we choose a softening length that is small enough, we can save the computation time and still be able to get a physically more realistic simulation. So if you ever see gravitational softening, this is sort of what they mean. Okay, but it turns out for the galactic center, we usually don't soften the gravitational force, once again, because usually stars are treated as point particles, and so close encounters become very important, and so we have to compute close encounters exactly in order to get an evolution of the stars near the galactic center that is dynamically interesting. Okay, so that was a brief aside on gravitational softening. Now I'm going to move on to orbit integration. So this is, now we have the force that we want on each particle. How are we going to get the new positions and velocities of the particles at the next time step? Okay, so in terms of orbit integrators, they're usually split into two types. So one is called direct integrators, and the other one is called symplectic integrators. So direct integrators, as the name suggests, is going to compute is going to do the integration pretty directly. So we're going to integrate out to a high order of the time step h, so that the error gets smaller and smaller very rapidly as we decrease the time step. So as you make the time step finer and finer, the error of the direct integrators get very, very, very small, and the accuracy increases dramatically. So an example of a direct integrator, a not very good one, is Euler. So this is probably the simplest one, where we just take the first order and stick it onto the direct integration and get the next time step. A better one is fourth order Runcutta. So I'll talk a little bit more about this in the next slide. On the other hand, we have another class of integrators called symplectic integrators. So symplectic integrators actually automatically conserve certain quantities exactly. So these are conservation laws like energy and angular momentum. We make sure that those are conserved exactly. And these are actually great for long-term integrations, because if we make sure that the energy is conserved or the angular momentum is conserved at each time step, we know that on the long term, the numerical integration that we've been doing is not too far away from the exact solution that we should get. So an example of this would be modified Euler or the leapfrog integration, and I'll specifically talk about the leapfrog integration soon. All right, so an example of a direct integrator is fourth order Runcuta. I'm sure you've seen this before, so I'm not gonna spend too much time on this, but I will walk you through the sort of method of computation. So fourth order Runcuta, as the name suggests, is going to include 4 evaluations of this derivative function at each time step. So the first one, K1, is going to be looking at the left endpoint, the previous time step, evaluating the function there. K2 and K3 are going to evaluate it at the midpoint. And then finally, K4 is going to evaluate at the right endpoint, the next time step. And then the value of the function at the next time step is going to be computed by doing this sort of weighted average of these 4 quantities, K1, K2, K3, and K4. And then the error is going to look like h to the 5th. So that's why this is called fourth order Runcuta, because this is accurate to 4 orders. And the general picture to have for fourth order Runcuta is as shown here. So at the previous time step, we're going to estimate the slope. So this is going to be K1. And K2 and K3 are sort of 2 independent estimates of the midpoint. And then K4 is going to estimate the right endpoint here. And so we're going to compute this weighted average and compute the next time step. And as you can see, even for this like sort of complex curved function, the fourth order Runcuta does a pretty good job of estimating what the next function's value at the next time step is going to be. One disadvantage of fourth order Runcuta and similar direct integrators, though, is the fact that we are not at all concerning ourselves with conservation of energy or conservation of angular momentum. And so the errors on those conservation or quantities that should be conserved are going to just keep growing without bound. So that sort of disadvantage of direct integrators is where symplectic integrators come to play. So the example of a symplectic integrator that I wanted to talk about is the leapfrog integrator. So I'll also walk through the computation of this. Initially, we're going to do a half leap in velocity. So using the velocity and the acceleration at the initial conditions, we're going to compute the velocity at the next half time step. And after that, we're going to do this weird thing where the position vectors are going to go a whole time step. But the velocity vectors are going to go each half time step, so to speak, using the acceleration at the previous time step. So this method, if you calculate it out, conserves energy, angular momentum, and phase space density, which are all things that are very desirable. So even though this is a second order integrator, because it conserves energy, angular momentum, and all of these things that we want conserved, this actually does a better job of sort of limiting the errors in the long run. But here's sort of the schematic picture of the leapfrog integrator, and you can probably see why this is called the leapfrog integrator. But from initial conditions, we calculate the velocity at the next half time step, and then from there, the positions are going to be at the whole time steps, and the velocities are going to be computed at the half time steps, as shown. Okay, great. And so this is an example of an orbit integrator that is used today. So it turns out that the distinction between direct integrators and symplectic integrators might not be as necessary today because we have this power to integrate it out to machine precision. And so IS-15 is an example of an orbit integrator that is used today. So this is a 15th order direct integrator, which is a very, very high order direct integrator. Excuse me. And it turns out that you can, deal with non-conservative forces. You can deal with close encounters, high eccentricities because of the high order of the direct integration. There's no problem there as well. Okay. And there's a paper, Rain and Spiegel 2014, that I've quoted here that investigates the systematic errors of IS-15. And it turns out that the systematic errors are well below machine precision. So we can compute these orbit integrators pretty much exactly out to machine precision, which is amazing. And another thing that is really great about IS-15, for example, is that it preserves the quantities that we want preserved, like the energy or the angular momentum, better than high-order symplectic integrators. So this is sort of the best of both worlds, a dream come true for dynamicists in terms of orbit integrators. So this is a high accuracy, machine precision, pretty much exact orbit integrator that exists today. Okay, and the final thing that I wanted to talk to you about is a little bit about hydrodynamical simulations. So instead of just having star particles, if we have gas particles as well, how does that sort of come into play? Okay. So the first type of hydrodynamical simulations is the Eulerian hydrodynamical simulations. So in this case, we're going to discretize space by using a mesh grid. So similar to sort of the particle mesh method, which is used for Poisson solving. But for Eulerian, we're going to discretize space by using a mesh grid. Eulerian tends to be more accurate, and it's also better at dealing with instabilities and shocks and things like that. But the other way of doing it is the Lagrangian method, which is going to be, we're going to essentially put a fluid representation of the particles, and we're going to discretize mass instead of space. So one advantage of the Lagrangian method is that because this is a fluid representation, the resolution automatically adjusts to what flow exists locally. So that is the advantage. Eulerian usually uses a common mesh, and so the resolution cannot be adjusted from place to place. And Lagrangians are usually easier to adjust for gravitational problems, specifically because of this resolution issue, right? If we don't already have this mesh grid in place, it's quite difficult to sort of impose the Eulerian and discretize space, but the Lagrangian and body hydrodynamical simulations can be directly added to your gravitational components. Okay, and the very last thing I wanted to talk to you about is smooth particle hydrodynamics. So this is the Lagrangian picture. But the issue is that gas particles are, of course, very, very small. And so even in a very, very tiny space, you have, millions and billions times the Avogadro constant number of gas particles. And so we can't really resolve gas particles individually. And so the way to deal with that, one way to deal with that is smooth particle hydrodynamics. And so this is what's schematically shown here. So instead of treating the particles as a point particle, which is very, very unrealistic to do that in an n-body simulation for gas particles, we're going to assume for each of the particles this sort of Gaussian profile instead of a sharp delta function, which is what a point particle is. So if we do this Gaussian, then essentially we can, add these Gaussians together to create a kernel for each of the gas particles. And so we can use this to go down to the particular precision that we want gas particles to be. And we assume some sort of smoothing length here and smooth out the particle's profile. And so the density profiles and the mass profiles sort of add more nicely in this sort of picture. Of course, this is not the most physically accurate possible way to do this, but this is one way of dealing with gas particles and sort of dealing with a more smooth fluid representation of each gas particle. Okay, so in summary, we talked about collisional versus collisionless n-body simulations. We saw that galactic nuclei should in general be collisional. We talked about Poisson solvers. So this is the tree method versus the particle mesh method versus the direct summation. All right, so in summary, we talked about collisional versus collisionless n-body simulations. So in general, we said that galactic nuclei must be collisional because of the small length scales that are involved. We talked about Poisson solvers. So we talked about the tree method and the particle mesh method as being the two sort of common simplifications. But unfortunately for the galactic nuclei, we are unable to use those. We have to usually use direct summation. We talked about gravitational softening. Usually the Plummer's potential is used. But for the galactic nuclei, once again, no gravitational softening can usually be used there. And finally, for orbit integration, we have direct versus symplectic. But galactic nuclei, as we saw, are usually directly integrated because nowadays direct integration does a pretty good job of conserving energy and angular momentum and things like that because of the high order accuracy and machine precision. So as you can see, the n-body simulations of the stellar sort of galactic nuclei is sort of the most hardcore way of doing n-body simulations. Everything has to be collisional, directly summed, no gravitational softening, and directly integrated. And then finally, as sort of an aside, we talked about hydrodynamical simulations and specifically went into the smooth particle hydrodynamics, which is quite popular these days as a way of doing a Lagrangian hydrodynamical simulation. And that's it. So thank you so much. And let me know if you have any questions.